Okay, section 3.1 on extreme values. This is our first section in chapter 3, and before we get into the new material, I just wanted to take us through what we've done so far. We talked about limits first. We did a numerical approach and a graphical approach, and there are a couple of pictures with an example of sorts of questions we looked at there. And then we took an algebraic approach. Continuing with limits, we talked about one-sided limits, which we did graphically. That was one approach. We also looked at piecewise functions. So here is our piecewise function over here on the left. And then we looked at the one-sided limit as x approaches 3 from the left of f of x, as the limit as x approaches 3 from the left of x squared minus x plus 1, and then we evaluate that function. And we use that part of the piecewise function because when x approaches 3 from the left, it means x is less than 3. So we use that part. And then similarly, we use 2x plus 1 when x approaches 3 from above because there x is greater than 3. So in this case, the limit overall would be 7 as x approaches 3. We talked about continuity. There's our definition that f is continuous at x equal a if the limit of the function is equal to the value of the function right there. And we talked about limits involving infinity. Then we moved on and talked about derivatives. That's, of course, what we just did the exam on right before spring break. Here's our definition of the derivative. Here we have the derivative at a point, and here we have the derivative as a function. But, of course, we are happier once we actually get to using derivative rules. Here are our interpretations of the derivative. We talk about the slope of the tangent line. We've done a lot of finding equations of tangent lines. We talk about instantaneous rate of change. And we've talked about the units of the derivative. And here we're using our Leibniz notation. The units of dy dx are the units of y, so that's the units of the function divided by the units of x, which are the units of the variable. And then we got into the derivative rules, and of course we have sum and difference, constant rule, constant multiple, power rule, exponential rule, product rule, quotient rule, chain rule. We talked about logarithmic differentiation and implicit differentiation. We talked about finding derivatives of inverse functions as well. But all of that really was about the mechanics of finding a derivative, not about actually using a derivative. And so in chapter 3, we start into moving into what we actually use the derivative for. And our first place where this happens is for looking at extreme values. So we're looking at absolute max and absolute min values. And that brings us to our first definition. A function f has an absolute maximum or global maximum at c if f of c is greater than or equal to f of x for all x in the domain. So this is the highest value we can possibly get for the function. The number f of c is called the maximum value of f. And when we talk about the absolute maximum, that is c, the actual x value. Here's a picture. Over here at x equal -3, we have our absolute maximum, and our absolute maximum value is 115. Similar idea for absolute minimum or global minimum. That is the lowest possible value the function can have. The minimum is at the x value c. The lowest value there is called the minimum value of f on the domain. And again, here's a picture. And in this picture, we see that at x equal 2, we have our global minimum, and the global minimum value is 1. Function f has a local or relative maximum at c if f of c is greater than or equal to f of x for all x near c. So in an open interval, an f of c is a relative maximum value or local maximum value of f. So this means because x is near c in an open interval, there has to be graph on both sides of the x value. And this might not be the highest point on the graph entirely, but is just higher than points close by. So going back to this picture we saw before, we saw x equals -3 is the absolute maximum. It is also a local maximum because this point, this height on the graph, is higher than any value close to it. But then if we look over to the right at x equal 2, there is also a local max here because this point is higher than any of the values, the function values around it. So we have a local maximum at x equal 2 and a local maximum or relative maximum value of 60. Same ideas for local minimum and minimum values. So we have f of c is less than or equal to f of x for all nearby points. And that's a relative minimum or local minimum value. And again, this is an example where you have to have graph on both sides of the point. So here's a picture, and on our picture we see at x equal -1, there's a local minimum value. At x equal 2, there's a local minimum value. And in this case, this local minimum at x equal 2, the local minimum value, there's -5, is also an absolute minimum. All right. Now we're going to get to some examples, and at this point, you should pause and follow the link in the slides without narration, or go to Blackboard, and you will see me give a video explanation of these two examples. All right, moving on to critical numbers and critical points. A critical number or a critical value of a function f is a number c in the domain of f such that either f prime of c is 0 or f prime of c does not exist. If c is a critical number, then the point c, f of c, is a critical point of f. All right, so now we're going to pause again. Follow the links in the slides without narrations. They will take you to the YouTube videos I have done for these 3 examples to find the critical numbers of these functions. You can also find the link in Blackboard for that. Then we get to a theorem. This is theorem 3.1.2 in the book. If f has a local maximum or minimum at c, then c is a critical number of f. And it's really important here to note, this does not mean that every critical number you get is automatically a local max or a local min. And now we get to our key idea from this section. It's 3.1.1. If f is a continuous function defined on a closed interval from a to b, to find the maximum and minimum values of f on the closed interval from a to b, here are the steps you need to follow. First thing you're going to do is evaluate f at the endpoints of the interval. In other words, you find f of a and f of b. Next thing, you find the critical numbers of f in the closed interval from a to b. And again, that means you're looking for where the derivative is either 0 or does not exist. But since we are only interested in the interval from a to b, if we find a critical number that is outside of that interval, we just ignore it. Next thing to do is to evaluate f at each critical number. And it's important to remember here that you're going to evaluate in the original function f, not the derivative function. And then the last step here is to find the absolute maximum of f. That is going to be the largest of the values you found from evaluating the endpoints and the critical numbers. And you're going to find the absolute minimum of f that's going to be the least of those values.